All right, let's dive right into this explainer on a revolutionary new AI-driven approach to treating sports injuries. We're talking about something that could absolutely change how athletes heal. If you've ever rolled an ankle on a run, tweaked a knee playing pickup basketball, or just dealt with that nagging tendinitis, you know firsthand how frustrating recovery is. It honestly feels like you're sidelined forever, just waiting for your body to do its thing. But today, we're looking at some source material that details a literal breakthrough in biomedical engineering, an AI-optimized treatment where a healing matrix is sprayed directly onto a wound. I know, it sounds straight out of a science fiction movie, but it is happening right now in the lab. To really grasp why this matters, we have to look at the sheer scale of the problem. Millions of athletes suffer from soft tissue injuries every single year. Sprains, strains, tendinitis, these actually make up nearly half, around 45% of all sports-related injuries. That is a massive chunk of the population dealing with damaged soft tissue every single day. So, whether you're a weekend warrior or a pro, the vulnerability of our soft tissues is a universal hurdle. But you know what's even more frustrating for anyone who loves being active? The recurrence rate. Up to 30% of these cases are recurrent, which means you get hurt, you go through that agonizing process of resting, recovering, you finally get back out on the field, and bam, the exact same injury happens all over again. It basically tells us that the initial healing process just isn't getting the job done. The tissue isn't bouncing back to its original strength, and athletes end up trapped in this vicious cycle of re-injury. So why does this cycle exist? Well, historically, we relied super heavily on the classic RIC protocol, rest, ice, compression, elevation, along with popping NSAIDs, your standard anti-inflammatory meds like ibuprofen. But these traditional methods have some pretty glaring limitations. For one, they are incredibly slow. And worse, relying on them carries some serious long-term risks, like fibrosis, which is the thickening and scarring of connective tissue, and even a heightened risk of full tendon rupture. Scientists knew they had to find a better way. The goal was crystal clear. Find a treatment that could be applied rapidly, deliver drugs straight to the targeted area, and actually promote regenerative healing instead of just masking the pain. And the solution they came up with? It is a massive leap forward. Researchers have developed a novel, thermosensitive, sprayable hydrogel loaded with the anti-inflammatory drug diclofenac sodium. Now, let's break down those terms really quick because they are key to understanding the whole shebang. Thermosensitive means the material literally changes its physical state based on temperature. Sprayable means it can be applied seamlessly to the weird contours of any injury. And loaded with diclofenac sodium just means it's acting as a highly effective delivery vehicle for a proven anti-inflammatory med. Now here is where the magic actually happens. Step 1, a medical professional or trainer literally sprays this formula right onto the injured tissue as a liquid. Step 2, it hits your skin and immediately starts absorbing your body heat. And step 3, this is the crazy part. Within exactly 45 seconds of reaching your 37 degrees Celsius body temperature, it transforms into a solid gel right there on the tissue. Just think about that. In under a minute, it goes from a quick liquid spray to a perfectly contoured, solid medicinal patch that adheres exactly to the unique shape of the injury. This instant transformation provides 3 simultaneous, totally game-changing benefits. First, as a solid gel, it immediately gives physical, mechanical support to the injured tissue, kind of like a custom microscopic cast. Second, because it contains that diclofenac sodium, it acts as a hyper-localized pharmacy. It delivers the drug exactly where it's needed rather than forcing your entire digestive system to process a pill. And third, it creates a regenerative scaffold. It literally gives your body's cells a physical structure to cling to and grow across, which actively promotes natural, rapid soft tissue healing. But hey, we have to pause for a second, because getting a liquid to perfectly gel in exactly 45 seconds, all while holding and distributing medication, that is not easy. The chemistry has to be absolutely flawless. If it gels too fast, it clogs the spray nozzle. If it gels too slow, it just drips right off the athlete's leg. So we really have to ask, how did they engineer this advanced biomaterial to behave with such incredible precision? Well, they didn't just rely on traditional trial and error. They brought in artificial intelligence. The researchers deployed a highly sophisticated dual model AI architecture. They combined artificial neural networks, or ANNs, with random forest models. The neural networks were trained on experimental data to provide absolute predictive accuracy for critical properties, specifically predicting the exact viscosity and the exact gelling time. Meanwhile, the random forest model stepped in to interpret the feature importance, basically helping the scientists understand why the AI was making the choices it made. It's this perfect marriage of machine prediction and human interpretability. And the impact of this AI integration, it literally cannot be overstated. By letting machine learning take the wheel, they accelerated the formulation development at a completely unprecedented rate. In the past, using traditional design of experiments methodology, creating and tweaking a complex hydrogel like this would take weeks of grueling manual lab work. By shifting to AI-driven optimization, they shrank that entire timeline down to a matter of hours. This data-driven approach dramatically cuts down R&D timelines and drastically slashes costs. Now, what's really fascinating about this formulation is the smart targeting of the drug release, which is completely pH dependent. When tissue is inflamed and injured, its pH level drops and becomes more acidic, sitting right around 5.5. Healthy tissue, on the other hand, sits at a more neutral 7.4. This hydrogel is so finely tuned that it aggressively targets the inflamed tissue, releasing 63% of its medication at that 5.5 pH. But if it touches healthy tissue at a 7.4 pH, it actually holds back, releasing only 36%. It essentially knows exactly where the injury is, concentrating its payload right at the source of the inflammation. Of course, none of this matters if the gel harms the body, right? Well, researchers confirmed through rigorous cell viability studies that the hydrogel is completely safe. The data shows it has moderate cytotoxicity with an IC50 of 180 to 200 micrograms per milliliter. In plain English, this metric just proves that the gel is biologically safe enough to act as that healing scaffold we talked about. It won't kill off the healthy cells trying to migrate into the area to repair the tear. It actually safely supports them. And beyond just healing, the team also tested its ability to keep the injury clean. Their antimicrobial evaluation showed a massive 43% improvement over currently marketed formulations. This is a huge deal. When you're dealing with severe soft tissue trauma, the absolute last thing you want is a secondary infection derailing the whole process. This hydrogel creates an impressive zone of inhibition, drastically reducing the chance of bacterial infection while the regenerative scaffold does its heavy lifting. Because this AI-driven approach is so incredibly effective at cutting R&D timelines and accelerating the jump to clinical use, the team has mapped out a seriously aggressive scalability plan. This tech isn't just staying in one lab. In year one, they plan to transfer this modular AI architecture to other biomaterial systems. By year three, they're targeting a cloud-based deployment of their AI models so other institutions can access them. And by year five, they aim to establish a global research consortium across 5 to 10 different universities. And that expansion actually leads us to the true overarching goal of this project. Ultimately, this isn't just about making an advanced medical spray for athletes, as mind-blowing as that is. It is about fundamentally integrating AI into the university curriculum. It's about preparing an entirely new generation of pharmaceutical scientists for an era of AI-driven drug development. By teaching students how to wield tools like random forests and neural networks alongside pipettes and microscopes, they are literally future-proofing the entire field of biomedical engineering. Which leaves us with this final, thrilling thought to consider as we wrap up this explainer. We are looking at a 45-second gel that drastically outpaces traditional medicine, built in hours instead of weeks, all thanks to artificial intelligence. If AI can optimize a hydrogel to heal a sprained ankle in record time today, what incurable physical traumas will it seamlessly repair tomorrow? The intersection of machine learning and human biology is just getting started, and the future of healing looks absolutely incredible. Thanks for joining me on this deep dive, and definitely keep your eyes on this space.